Yeah, 8 and 9 will be smaller than 10. So we can take this one step ahead. We can search this uh, in the next three, which is 12, 15, 17. But 10 does not exist here, cannot exist here, so it's not found. Took us 3 steps. So just by leveraging the knowledge of how an array is arranged, we can actually speed up our search. And so if we already have sorted data, then we can uh, solve it using some sort of a divide and conquer logic. Not really divide and conquer in this sense because we are just dividing the problem and we are not merging back the sub answers, but there is some aspect of division into it. At least that's how I relate to it, but then you can relate to it in your way. So the idea of binary search is you first need to know the starting element and the ending element. Basically, the positions, not really the values at this moment. Knowing the starting and ending positions of an array, you compute the mid position of the array. And then you check the value of the mid element with respect to what you want to find. Now, if the value you want to find is greater than the mid value, and the array is stored in an increasing fashion, then you know that it must be to the right of the mid value or at the mid value. Basically, it must be greater than equal to the mid value, right? Similarly, if you find that the value that you want to find is smaller than the mid value, then it must be to the left. Basically, you will be seeing every half tree. So within every half array. If it is in the first half, well and good, we'll search in the first half. If it's in the second half, we'll search in the second half. Awesome. Or it might be at the midpoint itself, at which point our search is ended. Very quick. Okay, so let's take an example of finding 12 here, let's say. Um, I don't know what they have these found. These guys have, I don't know, maybe they're finding 8, let's say. Okay, so the starting position is at index 0, ending position is at index 9. The mid of 9 and 0 is index 4. You can do it anyway, like you can do 9 plus 0 by 2, or you can do 9 plus 0 plus 1 by 2, but then you'll need to make it consistent. Whatever the rule you use, make it consistent. Here's the mid value, you found 4. Okay. Value at uh, value of stored in the array at this mid location is 7. We want to find 12. So 12 is greater than 7, which means that we don't need to consider the first 4 elements of the array. So we can discard that, which means that now we need to consider only the array from 8 to 17. We don't even look at 7 because, I mean, we check if the middle element is the same or not. If it's not, if it is, then we return, otherwise we exclude it. Okay, so now our array, the array that we'll care about is the one that goes from index 5 to 9, which means that the starting position is no longer 0, it is now 5. Now I can do the same logic for this array. So the mid element between index 5 and 9 is 7. Now the value at 7 is 12, which is equal to what I want to find. So I will say, okay, I found 12, returned, 2 steps, instead of the 7 or 8 that would have taken otherwise. If it is, let's say, as they've done 8, then what you would do is use update. You'll see that 8 is smaller than 12. So you'll discard this, the right subarray, that is 12, 15, 17. And you'll say that the ending node is now index 6 and your starting is same as above. So in any case, in this algorithm, in any case, what you do is you either update the start or the end. Or if it is found at mid, you just return from there. So this is how you formally write this algorithm. This is the first non-trivial algorithm that is discussed here so far. Uh, what you do is you have a starting position, you have an ending position, you find the mid position, check if the mid position is if the mid position has a greater value and your array is uh, whatever, ascending, descending. You can decide if you choose the first or second half based on whether it's ascending or descending. And then you update your start and end. So in either update, you will either keep one fixed and change the other. Otherwise, if the middle element is what you want to find, that's it. Return it and your search is finished. Keep repeating this until your start and end indexes are equal. Once your start and end are equal, it means that you only have one element left in your list. And if that element is not equal, then you cannot, uh, then it is not there. If it's not there, then it's not there. So that's it. So that was binary search. And you can also see how it will take login steps, because what you're doing is you're splitting every array into two chunks. So the first will, so if you look at it, the time taken for an array of size n is twice the time that will be taken for an array of size n by 2. And if you start solving this equation, you'll see that the time taken will be log of n. So this can be also solved in that way. This is the way that the booklet has solved for the complexity. So you can see. Okay, that was a bit too long for, I think, binary search. Let's speed up for sorting. Um, Once again, same problem. You have an array of data. You want to sort it in a given sequence. You want to put it in a given order. Now, it does not mean that you have to, like, let's say you have unordered data, 1, 5, 4, 3, 7, 8, whatever, and you want to sort them. Does not mean that you want to sort everyone. It might be it might be problem specific. Sometimes the problem will say, oh, we only want the first 5 sorted. Sometimes they'll say, oh, we want the entire thing sorted. Sometimes if you implement it from scratch by yourself, like when we are doing binary search, in which case you wanted a sorted array to begin with, then in that case you need to sort completely. So it is completely a decision on your side and on the problem side. But based on that, we can have different sorting approaches. Once again, we'll start with the simplest sorting approach, which is known as bubble sort. And no, it's not like that bubble popping thingy that you have, the bubble wrap. It's not like that. Yeah, so the idea of bubble sort is that you want to uh, like have you seen bubbles in water, how they float up to the top? So that's what the idea of bubble sort is, that you take the lightest element or the heaviest element and you float it to one side of the array, and then you do it for the remaining array. So in this case, let's say we have this array, for example. We start off with and let's say we want to make it I don't know, ascending order. So what we can do is we just need to move the heaviest element to the last position. We don't care about what happens to the others. We just care for the heaviest being at one end. That's what bubble sort's idea is. Always move the heaviest or the lightest to one end. Others don't matter. So, okay, how do you find it? Well, you compare. You compare with the neighbor. If it's heavy, you move it towards the end. If it is not, then you keep it there. So in this case, let's say you want to make it an ascending order. So ascending order would basically make it 3, 4, 5, 6, 8. That's the final order you want. So how would we do it algorithmically? At least in bubble sort. Well, you start up with the first position and you compare it with the neighbor. Always compare with the neighbor, immediate next neighbor, nothing else. So you say 3, but 3 is lesser than 5, so you'll swap it. Now you check 5 against 8. Well, it's smaller, so you don't care. Then the index of the third element of the third index is 8. You compare it with the one at fourth, which says value 4. Okay, 8 is heavier than 4, so we swap it. Now we've gone to 8. Compare 8 with 6. 8 is bigger than 6, swap it. Now you have 8 at the end. That was the heaviest element. Similarly, now you do bubble sort on the remaining four elements. So you check 3 and 5, no need to swap. Then you go 5 and 4, you swap. So this becomes 3, 4, 5, 6. Then you go to 5 and check it with 6. 5 is lesser than 6, no need to swap. 6 is at the last. Then you do the same between 3, 4, 5. Then you'll see that it is already sorted you do the same between 3 and 4, and you've already gotten your answer, right? So the idea is to find the heaviest element, one heaviest element for an array, and then move it to the end, which means that the first time you will go through the entire array once. So you'll go through all n elements. So n steps in the first iteration. The next time, since you fixed one element as the heaviest and you're not going to touch it, you're just going to see every other. Now you'll check over n minus 1 elements. So now you'll go over n minus 1 elements. Then you'll fix the second. Now you'll go over n minus 2. Then you fix the third, and so on and so forth. So at the end, the number of steps that you will take is 1 plus 2 plus 3 dot 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 n, which is n into n minus 1 by 2. So is that clear? And here's the thing. You remember we wanted to prove that it has to terminate? Well, the way we've defined it, it has to, because every time you're fixing one element that does not move, and that number of elements that do not move will keep increasing by 1 every iteration. This means that after n iterations, there will be n numbers that will not move or will not be swapped or compared, which means that after n iterations, this has to terminate anyway. N iterations over the entire array, I mean, not within, like, so there are 2 layers of iterations happening, which is why there's an n square. You implement it using a for within a for. So I meant over the outer for. So it has to terminate. You can see this as an example, actually. There's a better example for this. This is what I meant. There is one chain of iterations going on, which are iteration 1, 2, 3, 4. And within every iteration, there are sub iterations. So the iterations that I was talking about were these iterations numbered 1, 2, 3, and 4, not the sub iterations. So in this case, we start off with 6, 4, 1, 2, 5. We compare 6 and 4, swap. Now 6 is here. 6 is compared to 1. 6 is bigger, swap. Now we compare 6 and 2. 6 is bigger, swap. Compare 6 and 5, swap. Second array, the second iteration starts off with this array, 4, 1, 2, 5, 6. Swap, and so on and so forth. Finally, you will get your sorted array by the end of it. Number of steps this takes is 5, 4, 3, 2, which is 14 steps, which is n into n minus 1 by 2, how much? Like proportional to n square. So any doubts so far? Okay. Can anyone tell me what the is my complexity of this algorithm being n square? Is it correct, or can we like improve this, or can it be better in certain circumstances, or can it be worse in certain circumstances? Like, does anyone want to elaborate on it?
I think for the average case complexity, we can sort of keep counter that, okay, yeah, I've traversed through this array. I've not made any swaps. So I think I should stop all my iterations now. And here's your sorted array. Instead of going through all the iterations, all the n iterations, we could stop midway for the average case array, and thus bring down the complexity, bring down the time complexity to less than n square or something like that.
Fair enough. I mean, you'll have to design the logic yourself.
Yeah, so for example, in this case, in the third iteration, we already have the sorted array 1, 2, 4, 5, 6. But still we go on to the fourth iteration and we compare again. So instead we could just stop at this 1, 2, 4, 5, 6 in the third iteration. So we could design some kind of counter or stopper to determine where we need to exactly stop.
Fair enough. But basically, in the way this algorithm has been created, there doesn't seem to be any measures to reduce complexity, basically. Whatever we are suggesting, whatever we are discussing here is just an addition to the algorithm. So it'll be a binary search to a bubble sort 2.0, but not really plain bubble sort. So bubble sort really is unoptimized as an algorithm.
Yeah.
Yeah. Shardul had a question about why the number of iterations reduced by one, like why the number of sub iterations reduced by one every time. Well, that's because remember we were fixing the heaviest element at the end. So, for example, here when you go through the first iteration, you fix 6 at the end. Now you've compared between every possible pair that can be. You've chosen the heaviest element. So obviously nothing is going to swap with 6. So if you want, sure, you can do a comparison here, but it's a wasteful step. Why do you want to do multiple wasteful steps? So you won't go over this entire, you will, for all intents and purposes, the 6 does not exist for you now anymore. Similarly, here also, this 5 and 6 no longer exist for you. 4, 5, 6, and so on and so forth. If you want, you can, but then this is even worse in terms of optimization. It takes even more time. Yeah. Right. So a lot of people have answered it correctly in the chat. So let's go on to a similar worst case complexity sort algorithm, but a better algorithm in certain cases. Like for example, we were discussing about bubble sort, and it seems like the way the algorithm is designed, you go with any way and you will end up with n square. It's not really a good algorithm. But can you go to a O of n or O of something lesser than n square in a best case or in a specific case? You can. And that is insertion sort. Once again, a simple logic behind it. You have an unsorted array, let's say 6, 4, 1, 3, 2, 5. What you do is, and there are multiple ways of doing this. I'll just go with the simplest way of doing it, which is taking a lot more space, but then you can do it using in the same space, but you can make it more efficient. I'll go with the simplest way. You have an array of size 6, which is unsorted. Create an empty array of size 6. Okay. In this, you take the first element and you put it in the empty array. So now your empty array will have 6. Your unordered array has 6, 4, 1, 3, 2, 5, but your empty array has 6. Okay. Now you go to the second element of the unordered array. It is 4. You add that to the empty array. But now you sort the empty array. Okay. So you check 6 compared with 4. 6 is bigger. So you swap. So now it is 4 and 6. Okay. Now you go with the third element of you go for the third element of the unordered array. You see it's 1. And now you once again add it to the empty array, to the second array basically. Now it's 4, 6, 1. Keep comparing until you find the position of 1. So then it becomes 1, 4, 6, and so on and so forth. On the face of it, it seems that you're doing one operation here, two operations here, 3, 4, 5, so on and so forth. So it seems that essentially you'll be doing O of n square operations once again. How is it better? Well, uh, sometimes it can actually be better, especially when uh, let's say you want to create an ordered subarray. Let's say you want to maintain the top 3 elements here. You only want to keep the top 3 elements sorted. Everything else does not matter to us. So in this case, let's say you get 1, 4, 6. You check for 3. It comes in 1, 3, 4. We don't care about 6 at this point. Okay, it takes 2 steps. Then you check for 2, put it there, 1, 2, 3. Okay. Then you check for 5, it's bigger than 4. We don't even do a check at all. So in such situations, insertion sort can give you a linear complexity, because in this case, as this array is sorted and you want to add a element to a sorted array, you don't need to do a pairwise check and swap, and do it in multiple times. You just need to iterate it once and find out the position where it needs to be added. And if your array has some structure, if it is a bit sorted, or if it follows a certain distribution, insertion sort can be linear. So this is what I have defined here. This is what I have detailed here. The steps, I've written them in a proper format, I would say. But so the total so see, on the face of it, it seems like the complexity is still again going to n square, which is true, but this is the worst case. If there is some sort of an ordering, or if you can restrict the number of ordered arrays, then you can actually make it a linear addition. So insertion sort can be useful if you want to, okay, as the name suggests, if you want to insert into a sorted array and keep the sort order. In that case, it becomes a very efficient, rather efficient algorithm. Does anyone have any doubts though? Because it's a bit tricky to understand at times. Are there any doubts? Okay, doesn't seem like it. Seems like people are generally clear on insertion sort. Okay. Can you explain insertion sort again? Binary search for the insertion step. Then it might be n log n. Sure, I mean, that can be an optimization you do, but okay, I mean, you can add in log n steps instead of adding in n steps. Sure, fair enough. I mean, you can make variants however you feel like. Sure, so I think that's fine, but I don't think it stays. I don't think the n log n thing applies overall to this algorithm really, because let me think about it. You're adding an. I mean,
The array is actually not sorted, so we cannot use binary search. Means for
actually, I
the
mean, yeah, no. Like if you're adding to the sorted array, like for example, he was actually saying that if you're adding an unsorted, if you're adding a random element to the sorted array, then you can actually do it in.
Hello.
But actually, yes, binary search will be searching for. I mean, that element will not be present in the sorted array, right? I mean,
Like
what?
I was saying, like if we have a long array, like around 1000 number array, which we want to sort, and we
Uh-huh.
are like halfway through it, and like
Right.
the first 500 numbers are sorted already, and the 51st number we want to insert. So for inserting that, rather than comparing with each of the 500 numbers, we can
Mm-hmm.
compare it with the mid value, and then find whether it is less than or greater than, and so on, like that will be logarithmic rather than linear.
I mean, sure, you can constrain it that way, but I still don't see whether if it'll work in practice though. I get your point. I'm not sure about it though, because I think I have tried similar implementations at times, and they always have some flaw. Let's think about it. I'll think about it. I'll get back to you on this. If anyone has any rebuttals, so they can also, or any support also.
the next half part is not sorted, so we cannot actually apply binary search. Means
Yeah, I
we
mean,
might
it's. I think he's saying that you're talking about only the sorted part, not the unsorted part.
no.
So
He said for means for the next 500 elements, we will start searching from the middle of that next 500. So
No,
if that
He was
like
saying that 500 are sorted. If you want to add 500 and first, then you can do some sort of a binary search within the first 500 and then add accordingly. So the first 500 being sorted can allow you for binary search. Is that what you're saying, Shreyas?
yes, that was what I was saying.
Yeah. So that
so
actually is, yeah. Please.
can I say something?
Yeah.
Um, I think matlab, his argument is right because with each step,
Hmm.
so the time complexity is increasing. Like the first step will take log of one, then
Hmm.
second log of two, log of three, log of four. It will essentially become log of n factorial, and that can be upper bounded by n log n.
It'll not be log of n factorial, will it? Uh,
You're adding, right?
yeah, wait a second. So first step is taking you log of 1 and log. All right. Yeah, log of n factorial. Yes.
So
So log
that
of n factorial n log
can
n.
can be bounded by n ki power n. So n log n, the upper bound.
Yeah. Yeah, that makes sense to me. I just think it's a variant of insertion sort, I think. Not the vanilla insertion sort algorithm. Yeah, there's a thing called as binary insertion sort. I think that's what you're talking about. Yes. See, yeah, that's what I found out right now. Binary insertion sort is basically what you're describing, Shreyas, that you use binary search to find out where to do the insertion.
Oh,
This
okay.
is, yeah, so this is a different algorithm. Basically, it's a improvement on insertion sort.
Oh, okay. So the order will be like n log n only.
Yeah.
Of
The order will be n log n, but it's not
okay,
vanilla insertion sort.
okay.
Yeah, but it's good that you're spotting all this because you're creating your own algorithm. So that's a very good thing. A lot of places where I found this useful is especially where you have priority based questions. Like if you want to have a priority queue of, or like if I don't want to maintain a priority queue or something, and if I want to maintain top 5 elements, top 10 elements of top 10 most frequently occurring words, let's say in a dictionary, then I can just keep 10 sorted, and then every one I can do an insertion sort for addition. That makes it very efficient at times. Depends on your problem once again, but good that you pointed this out. Right. Let's go on to another n-log-n algorithm. It's something that we've discussed from the heap data structure. So it's heap sort. And I think I discussed this within the heap data structure as well, that whenever we are removing from heap, we are actually just concerned with the root element. We just remove one element when we're removing from heap. So that takes one step, and then to rebuild the heap, it takes at max log n steps. You do that for all elements. At the end, you will have no heap left, which becomes, at worst, it becomes an n log n algorithm. But I think a lot of people might not know what heaps are if they've not attended the data structures thing. So a quick recap, heaps are a form of trees in which every parent has a relation, in which parents have a relation with children. Children don't have relations with each other. Okay. Parents can, either the parent node values are larger than the children nodes or the parent node values are smaller. If the parent node values are larger, it's a max heap. If the parent node values are smaller than the children node, it's called a min heap. And because there is some sort of an order in this, when we are adding elements to it or when we are removing elements to it, this can be done in a logarithmic number of steps. For more details, refer to the booklet or the previous lecture slides. But yeah, so for example, so once you have a heap, so let's say you're given an unordered, let's say you're given an n element array, which is not sorted. You take every element one by one and you build a heap. That will take log n steps. Okay. Now you take the first element out. It will be the maximum element because, I mean, it kind of has to be the maximum element, right? Every parent will be bigger than child. So the max heap will have the largest element at the top. Okay, so you remove one and then you rebuild the heap. So basically, you take the parent element, remove it or move it into some other array, and then take the last element of the heap and move it to root and then bubble down. And then once you have the new heap, then you take the root element again and put it into the second array and then bubble down and so on and so forth. So first time you take log n steps to build the heap, second time you take log n minus 1 steps to rebuild it, and log n minus 2 and so on and so forth till the end you take log 1 step. Now multiply this, like add this. So log 1 plus log 2 dot log n is log n factorial, which is bounded by n log n. So that becomes your complexity of doing heap sort. And this is extremely efficient. Plus, this is very easy to build because you only need to write this shift down and heapify functions. And basically, if you implement heaps, you kind of get heap sort for free. So if your question involves priority queues or heaps, then heap sort is the natural way to go. Any doubts on heap sort though? Okay, so let's go to merge sort. Merge sort is a similar algorithm in terms of complexity, in the sense that it is n log n, but I find it a bit uh, okay. I mean, I find it a bit weird to implement, although you guys need to be very sure about this, uh, because it's possible you might need to use merge sort a lot, and it takes a lot less space than heap sort. So yeah. So what do we do with merge sort? It's a divide and conquer algorithm, which means that if you want to sort an array, the problem is equivalent to take the problem to sort an array can be split into two parts. You sort one half of the array and you sort the other half of the array. Then you merge these two and sort them. But you can do this until you have smaller and smaller and smaller arrays. At the end, you will have only one element arrays, which is essentially just one number. Now, what you do is you start merging these one numbers back into an array form. Just that while we are merging them, these merges need to be done such that the overall merged array is sorted. What do I mean by this? For example, you split your array into these 6 numbers. Now, let's say you're looking at 1 and 5. Now you're merging 1 and 5, you get 2 and 5. This is sorted. Now you want to merge it with 3, you get 1, 5, 3, 1, 3, 5. If you had just merged right away, then it would have resulted in the same array. So that's not a benefit. How would you do this? Well, you have 3 elements here. So you would iterate from the first you keep 2 pointers. One pointer for the array 1, 5 and the other pointer for the array 3. Point as in any number or counter, whatever. And then you iterate over the total sum of these counters. So at counter 0, the value is 1. And at counter 0 for the second array, the value is 3. 1 is smaller than 3, so you choose 1. Update this counter. Update the counter of the first array. This becomes the counter next points to 5. Now at the second step, you see, okay, 3 is smaller than 5, so you choose 3. And then you choose 5. So it basically takes an iteration of 3 steps. Similarly, you do that at 4 to 6. It takes an iteration of 3 steps. And that is how it'll and similarly, this is how you would do it with when you're merging 1, 3, 5, and 2, 4, 6. This will have 2 pointers. First pointer is pointing to 1, second is pointing to 2. Now, when you're merging, you see the value at first pointer. This is 1. Okay. And this value at second pointer is 2. Which is smaller? 1. You put 1 in the final array. Now, pointer 1 will point to the next element of 1, which is 3. Okay. So pointer 1 is pointing to 3. Pointer 2 is pointing to 2. 2 is smaller than 3, so you choose 2, put it in the array, and move pointer 2 to the next, which now points at 4. Now pointer 1 is pointing at 3, pointer 2 is pointing at 4. Choose 3. Then you choose 4 and 5 and 6 and so on. It's taken 6 steps. So if you want to do a complexity analysis of this, you can see that every merge can take n steps, but then there are log n number of merges. This is a very rough offhand calculation. You can do it in a much better way, but a rough calculation would say that there are n steps in a merge and there are log n number of merges that will happen, because if you divide something, because number of merges depend on the number of depth levels in some sense. So total number of steps that will be taken will be n log n. This is a very hand wavy calculation, but you can do this in a more mathematical rigid way. You'll still get an n log n as the number of steps. So any doubts on this? Merge sort can be a bit tricky, really, when it comes to implementation. It's also implemented recursively. So the way you would say is that, let's say you have a function, merge sort, which takes an array as an input. What it'll do is it'll take a midpoint, divide the array into 2 parts, and then call that merge sort function on one half and merge sort function on the second half, and then it'll just say merge. So the idea is to perform the same steps on every half. So recursively, it becomes very easy to implement. Iteratively, it would have taken a lot more, a lot bigger implementation. So any doubts that anyone has?
So when we are actually merging the any two given subarrays, so we'll need to use some kind of sorting algorithm to actually merge those two subarrays, right? So what kind of sorting algorithm do we actually use in this case?
So it's not a sorting per se, like it's just a two-pointer approach. Like for every subarray, you maintain one pointer. So there are two arrays, two pointers, and then you just iterate from 0 to the total length of the merged array. So the sum of the two subarrays. And whichever pointer has lesser value, you just take that.
Okay, great, cool, got it. Thank you.
Yeah. In fact, this approach, so all these algorithms, they involve some approach, some sub-approach in them. If you mix and merge these approaches, it can become very useful. So for example, this two-pointer approach that I mentioned, that is used in the merging of the two subarrays, you can use this two-pointer approach to also add two sorted arrays. In general, in life, you can use that to add two sorted arrays to form a sorted array. This complexity will be n, because two pointers, each of them will be running over their respective sorted array, and the total number of steps will be the sum of lengths of the two arrays. So this can be a sum of two sorted arrays can be done in n steps. You don't need n square or anything, because you know that the arrays are sorted. So this two-pointer approach is also very important. Do keep that in mind. I will not be discussing any other sorting algorithms beyond merge sort. Not that there aren't any. These four are the ones that are most complicated. These four are the ones that are most generalized or general to discuss in a way. There are a few algorithms though that are very useful. So there's an algorithm that you call counting sort. There's also an algorithm which is called bucket sort. So these counting sort, bucket sort, two-pointer, three-pointer approaches, like we took two pointers to merge two sorted algorithms. We can also take a three-pointer approach. Yeah. But yes, do look at those. I also have a very interesting article about how you can solve one question in 7 different steps and the complexity that can change. So for example, this one person, he started, in fact, I'll just uh, show that to you in this, if I can. Google, it seems to be not yeah, I guess once I find it, I can actually share it with you. Anyway, let's just go on to graph algorithms. So remember last time we were discussing graphs for those who were here basically, and I didn't give you any specific implementation of graphs. All I just said was graphs are useful because they are a very generic representation of data, and the biggest strength of graphs is are the algorithms that we apply on those graphs. So now's the time to actually discuss the algorithms that can be described, that are done commonly on the graphs. These ones are the most important algorithms I think that you'll come across, because your interviewers will also ask these algorithms. A lot of problems can be boiled down to these graph algorithms. So you need to be very clear on those. Okay. So depth first search, right? Depth first search, the idea here would be that take a starting point and you go until its very end. Then once that entire subgraph has been explored, you come back and then you explore another subgraph completely. Basically, the idea is that you want to do a full depth exploration of every subgraph. Let's say given a starting node, it is connected to different nodes and there can be some structuring or whatever. What you want is you want to explore every subgraph that covers, but in full depth first. And then you just come back, go on until do the same for the second, do the same for the third, and so on and so forth. So, okay, I don't think it's been updated really, has it? Yeah, it hasn't. Yeah, right. Yeah. Wait, my screen. Okay, sure. So, how would I? Let's say let's see an example of depth first search. How would you say it? Let's say you have a maze problem. Yeah, you can do it. Let's say you have a maze problem. Let's say you have a maze and you are standing in one position of a maze. So I'm pretty sure all of you have seen mazes, right? Like in Harry Potter and everything. I'm pretty sure you've seen maze, like in the Triwizard Tournament finals and everything. So let's say you're standing at one position of a maze, and you can essentially plot every point as a graph node. Some of them which cannot be reached, some of them which are connected, and so on and so forth. Let's say you want to find out the maximum length of maximum number of steps that you can take in given a starting point. Assume that the maze is closed, there is no exit. What you can do is, given a starting point, you can explore one path completely till the end, and then come back and then explore the other path, and so on and so forth. Right? And the one that has the maximum length, well, you say, okay, this is the maximum length maximum number of steps that I can go through. What's important here is that you need to be able to see if you've already been through a subpath or not, because then there's a problem in graphs called cycles, in the sense that there can be graphs which connect back to each other. Let's say here, if nodes 2, 4, and 5 were connected. Here, for example, in this figure, 2, 4 are connected, 2, 5 are connected. But let's say 4, 5 are connected. So if you're going from if you're going from node 1 and you want to go into its complete depth, you'll say, okay, 1 will go to 2, 2 will go to 4, 4 will go to 5, 5 will go to 2, 2 will go to 4, 4 will go to 5, and this will go on, so on and so forth. This is a problem. So what we need to do is we need to ensure that we keep a list of all the arrays that have been visited, of all the nodes that have been visited, and let that be a property of the node. So we won't visit any node that has already been visited. In fact, we'll just stop there. So we go to 1, okay, 1 has been visited, 2 has been visited, 4 has been visited, 5 has been visited. Now if you go to 2, cannot go because it's already been visited. This exploration is gone. Now because 1 is starting, go to another one, 3. Okay, 3 is visited. Oh wow, you've explored the entire graph, right? Right. So this would be how you would do actually depth first search. You go into complete depth once, and that's it. I mean, you can solve a lot of maze problems with it. Actually, I'm not able to find a good problem actually to share with you, but okay. No worries. I think you can find a lot of depth first search problems on Geeks for Geeks, but that's the idea. Now contrast that. What else can we do? How else can we go through this? Well, we can go through it in a breadth first search fashion, which basically means that you go as wide as possible. So you'll say, okay, we are at node 1. What all are its neighbors? Node 2 and node 3. Add them to a queue. Okay. Then you remove one element from the queue. Okay, one has been visited, all its yeah, so implementation wise, I'm actually going into the implementations. Okay, no worries. Let's say you want to explore this without going into the depth. Let's say you want to figure out the distance between two nodes. It's essentially a shortest path between two nodes. You can see that in depth first search, you will not probably get the shortest path always. Because if you want to say that what's the distance of node 5 from node 1, assume that 4 and 5 are connected. In that case, you'll go from 1 to 2 to 4 to 5, or you can actually go from 1 to 2 to 5. In either case, you can get one node with a distance of 3 and one node with a distance of 4. which means that you do not really have a nice representation of how far or what's the shortest distance between these two nodes. Instead, you can go in a depth-wise fashion, which means we start off with node 1, its neighbors are 2 and 3. Okay, all the neighbors of node 1 are visited, mark it as visited, we don't care. Now nodes 2 and 3. These have a distance of 1 step because they were the immediate neighbors. Now take any one of them and start looking at its children or its neighbors, basically. Not really children because graph will not have a concept of children. Its neighbors. Okay, 2 has neighbors 4 and 5. Add them to the queue. Also, because 4 and 5 are the neighbors of 2, which was the neighbor of 1, it means that the distance of 1 from 4 or 5 is 1 more than the distance from 2. So the number of steps it takes from 1 to go to 4 or 5 is the number of steps it will take from 1 to go to 2 plus the steps taken from 2 to go to either 4 or 5, which means 2 steps, which gives a correct answer for the shortest distance. That's where BFS is better than depth first search, right? So that's the logic behind it. Like you just go from one node and then you go layer after layer, like immediate neighbors, then neighbors of neighbors, then neighbors of, like for example, if you would go on Facebook, share privately, share with friends, friends of friends, friends of friends of friends, and so on and so forth. So this is how you would actually go. How would you implement depth first search or breadth first search? Is something I'm interested in. So anyone can unmute themselves. If you also have a doubt, please unmute yourself and ask, at least regarding DFS, BFS, because these are very important. Anyone?
I think what we would need to do is we would need to first of all store a graph. So we can take a node, we can define a data structure called a node and define a data structure called edges. So we can we can store the graph in the form of nodes and edges, or rather we can create an adjacency list or an adjacency matrix. So now we'll traverse through the nodes. We'll find, suppose say we have a node A. Now we'll find out what nodes is the node A connected to from the adjacency list or the adjacency matrix. Now we'll select the first connection and move on to the next node. And now for the next node, say node B, we'll again check which all nodes is it actually connected to, and then move on to the first node we find. So we'll go on. And once we reach a point where it is not connected to any node, we'll go back and start from and begin this process again, or rather repeat this process. Yeah.
Right. So essentially, a recursive or an iterative solution, right? So usually I prefer like there's a staggered approach really. For one of these, recursive is much natural. So for depth first search, I think recursive is more natural of representation. For breadth first search, for example, queue is the way to go. Like every node you take, its neighbors you add to a queue, and then and you mark it as visited, and then every node in the queue you actually will pop one of them out and see its neighbors, add those to the queue, update the distance measures, and if they are visited, then basically you don't update the distance. Otherwise, you update the distance, and so on and so forth. Eventually, the queue will be empty. I think BFS is simpler to implement than DFS, but the implementation should be in your booklet. So do try and implement those yourself, though, without seeing the booklet and just thinking of this idea. Maybe look at it as a queue point of view for BFS, and DFS actually you can also take as a stack approach. Not really, but you can think of it that way. So any other suggestions, any other doubts that people have regarding BFS, DFS? Also, Kunil, I mean, your method of representing a graph is very generic in the sense that it is generalizable. It is completely perfect. Like it has nodes as a data structure, and you have edges, representation and everything. But honestly, sometimes it can be overkill. Like this is a bit too it might be a bit complicated for a lot of CP problems. Sometimes it's just easier to maintain a 2D array.
Yeah.
So I mean, it's all okay. I mean, it's just that never make your implementation so complicated that you make some implementation error. Like we don't want seg faults and TLEs and all that just because some implementation errors there. But yeah, otherwise it's perfect.
Cool. Thank you.
Cool. So okay, no one else. Anyone else? Yeah, Shruti has suggested a link regarding this. I think you should see that, everyone. Okay. Right. Let's. Okay, there's another graph which shows you. So the difference between these. Okay. Finally is Dijkstra's algorithm, which you want to use to find shortest distances between two nodes. So the thing about Dijkstra's algorithm, however, is that it will only work if the distances are positive between like every pair of nodes. If there's anytime if there's a negative distance, it will not work. Because what we're relying on is that we're relying on using a minimum function, like minimum of two distances. So for example, you will have a distance as an array. You'll maintain a distance array and you'll maintain a visited array. And that distance array is initialized to nothing or -1, whatever, or max, int max, or whatever you want to do. And you'll have a visited array. That visited array will keep track of whether you've visited or. In fact, you don't even need it. If the distance array has some non-initial value, then it is anyway been visited. So you start off with a starting node and you start populating the distance array based on based on all the other nodes that you can reach from there. So let's say you start off from node 7 and you want to find out distance till node, I don't know, 5, let's say. Okay. So you will have there are 4 neighbors of it, which are 1, 0, 8, and 6. Now you'll say the distance of 1 is 11. Because we are just looking at from node 7. Let's say distance of 1 is 11, distance of 8 is 7, of 6 is 1, of 0 is 8. Okay. Now you can go through, now you find out the least of these, which is here, 1. Now you'll say, okay, distance of 8 is either 1 plus 6 or 7, whichever is the smallest. In this case, it's the same. So you'll say, okay, it's 7. Distance of 5, you'll say 1 plus 2 is 3, and that's it. So now the distance array will have 3, 7, 8, 11. Now you'll see the smallest is 3. So distance of 5 is 3. Okay. Now you look at all of its neighbors that have not been visited. So 4 will be 3 plus 10, 13. 3 plus 4, 3 will be 17. And 3 plus 4, 2 will be 8. Right? Now you have a certain number of elements here which have some distance. Then you'll find the minimum and then you'll try to go to every node. So eventually there'll be a time that you will have a distance, you'll have an entry in the distance array for every node. And what you need to do is you need to check if the entry that is already present is smaller, or if the updated entry that you can provide at a given step, that is a distance to the current node plus the distance between those two nodes, is smaller. Whichever is smaller, that is the shortest distance, and the path will change accordingly. Clearly, you can see why a negative number will have a problem. Because if, let's say, this was -1, then with every time you go on this path, you will reduce your distance by 1. So what will happen is everyone will want to go through this path infinite number of times, and this algorithm will never converge. So Dijkstra's algorithm can help you find distance between the shortest distance between one node and other nodes. Right. Any doubts for Dijkstra? Okay, doesn't seem to be any doubts for it. Okay. So clearly there's one problem with Dijkstra, which is that it'll not work for negative path length. It'll not work for that. If there are negative path lengths, we can actually use the alternative algorithm, which is Bellman-Ford. This, however, is the complexity of Dijkstra actually is much smaller than Bellman-Ford. Bellman-Ford is much of O(n) cube order. Dijkstra is lesser. And Bellman-Ford will actually implement this using multiple for loops, so for and for and for. But I am actually not very interested in, I've just mentioned it here that Bellman-Ford is one algorithm which handles negative weight edges, but I'm not very interested in discussing Bellman-Ford per se, because I haven't seen it used a lot, honestly, at least not in interviews or anything. And Dijkstra is one that we usually go for. Plus, a lot of times you can always reformulate your problems to look like Bellman-Ford. So this I would actually assign to you as further reading, not really a part of the lectures. There are also other algorithms that I would want you to see as part of further readings. These involve minimum spanning trees. I have shared a few resources. And minimum spanning trees I have mentioned as a further reading because they are not very useful at this level, I guess. I have not seen a lot of people ask questions on these. The most common are actually BFS, DFS, and Dijkstra. So yeah, any questions until this point? Any discussions or any doubts or anything?
Where would we actually use edges whose weights are negative? I mean, I can understand the logic behind positively weighted edges, but where do we actually use negatively weighted edges?
Interesting. Okay. Actually, it depends on how you want to formulate your problem. Like if you want to formulate it in terms of distances and everything, sure, it'll always be positive weight edges. That's why I'm actually not. That's actually one of the reasons why I was not discussing Bellman-Ford, because a lot of real world problems can be solved by Dijkstra. The fact that you have positive weight edges. But would anyone like to think about where you could have a negative weight edge? I mean, I guess if you want to represent
like
directed graph, maybe.
Yeah, like maybe going from B to D is different from going from D to B, something like that. Like the magnitude is same, but the weight maybe.
Yeah, maybe like the direction is causing
Yeah.
a negative edge to be there. I mean, sure, you can say that, but then that
Or
problem
maybe
can
we
be
could think of it in such a way that there are two paths. One from B
Right.
to D. B to D is a one-way road, and now if you want to go back to B from D, you'll have to take another path whose distance is something else. So you can add a negative weight to include a direction as well.
But I mean, this can be reformulated in a Dijkstra way, right? For example,
Yeah.
if there is a different direction that is given a negative value, you can just remove it from the adjacency list of the one, and you can just make the adjacency list as a asymmetric matrix. In that case, you can still get a positive weight and only apply Dijkstra.
True.
There might be cases where I mean,
Like
I
while
don't.
playing a game, if we choose a certain path, we will gain health, and if we choose another path, we will lose health. Like,
Yeah, this guy plays. This makes sense. Yeah, you're right. But I mean, yeah, sure. Abstract we can discuss anytime, like why this will happen, but usually, yeah, transaction of money. That's a good idea. Okay. Okay, so we have a question from Chandrasekhar, which is that if you write a recursive algorithm which has n levels and the inputs to algo are all O1 in memory. Okay, so let's say, okay, what is the memory complexity? So can you clarify this one? GCD algorithm, let's say. What's the memory complexity of GCD? I mean, the way we are solving a GCD problem is actually just taking that same memory and it is just rewriting over it. Plus that recursion is not really being split into multiple. I mean, okay, so when you're talking about recursive algorithms and the benefit of DP and, for example, complexity increasing over time for memory or anything, you should also be careful about how that recursion is implemented. For example, if that recursive function just calls itself once, then then it will not be causing a problem that you can use DP for, or that will increase your memory complexity a lot. Because function A runs, calls itself, runs again, calls itself, runs again, calls itself. Only the memory of the elements that are allocated beyond the recursive call, which are not triggered immediately, they will keep stacking up. So this becomes easier to model, even in terms of time complexity. If your recursive function is calling more than one, calling itself more than once, or if let's say there are cycles, then it is where your complexity diverges to become an exponential. You can think of it as like 1 to the power of k stays as 1, but 1 plus x, where x is positive, to the power of k diverges. You can think of it as in that sense if you want to. Can every recursive algorithm be written using stacks to avoid some error regarding large recursion sizes? I mean, eventually a recursive function call will be implemented on the computer using stacks, right? So I mean, the problem is you might get a stack overflow. If